The first related rates problem we're going to take a look at is really a classic. And this problem involves a ladder that's sliding away from a wall. So first let's draw a picture of this situation. So we have some sort of wall, and then we have a floor, and then we have a ladder that is leaning against a wall like this. So that's the physical situation. So we have a ladder that's leaning against the wall. So, and it's a 5. So we have a 5-foot ladder that is being pulled away from a wall at the rate of, let's say, 1/2 of a foot per second. So the ladder, basically somebody's pulling the base at 0.5 feet per second. So the problem says determine the rate at which the height is changing at the moment when the foot of the ladder is 3 feet from the wall. Okay, so this is all the information. So basically, okay, we're looking at the moment when the foot of the ladder is 3 feet from the wall. So that we have 3 feet like that. Since the ladder is 5 feet, the height has to be 4 feet like this. So height, we just mean the distance between the top of the ladder and the ground. So we have a 3, 4, 5 triangle, and we have to find the rate at which the height is changing at the moment when the base of the ladder is 3 feet away from the ground. Now in my strategies video, I mentioned that in certain problems, some of the numbers are going to be just flat out constants, and other numbers are just going to be the instantaneous value of a function that's changing in time. So here, the constant is going to be the length of the ladder. So this is basically a constant. The length of the ladder is not changing as a function of time. Now, since we're pulling the ladder from the wall, the 3 and the 4 are only instantaneous values of those quantities at that particular moment in time. Right? So the base of the ladder is being pulled from the wall at a given rate that's indicated, and we're trying to determine what the rate of the change of the height of the ladder is from the wall at that one moment. So it might be that this 0.5 feet per second might itself be changing. This is the value of that rate of change at that particular moment in time. So the next step, we've read the problem, we've assigned variables. So the next step is we wrote down the information from the problem. So our next step is to assign our variables. So we'll let x be the distance between the wall and the foot of the ladder. And then y is the distance between the ground and the top of the ladder. Now, it's a good habit to always list your assumptions. So if I were to write this up formally, I would probably say assumptions. And one of my assumptions is that the ladder is not losing contact with the wall or with the floor. So we're pulling it, and the ladder is just gliding down the wall as we pull it. And I suppose the fact that the ladder is only 5 foot in length, the fact that that length is a constant, is also an assumption. Maybe it's an extension ladder. Maybe that assumption is not valid. So it's always useful to track down your assumptions, because later on when something goes wrong and you've realized that there was a mistake, you can go back and look at your assumptions and say, which one of these assumptions must have been wrong. And assumptions are usually very, very subtle. So it might take a little bit of practice or a little bit of thought to say, what are the underlying things that I don't necessarily know for sure? That if I find out my answer is wrong later on and I did all the work correctly, maybe one of my assumptions was erroneous. So basically x is this length and y is this length. So basically x at this moment in time, let's just call it time t equals 0, is 3, and then y of 0 is 4, and then x prime of 0 is 0.5. Now x and y are functions of time. Right, so the independent variable is always time with these related rates problems. So x of 0 is 3, y of 0 is 4, the x dt at time 0 is 0.5. And for the 0.5, I need to do a check in my mind. Is x really increasing? Well, the problem says that I'm pulling the foot of the ladder away from the wall at a rate of 0.5 feet per second. So that means that that distance is going to be increasing, so dx dt should be positive. If we were pushing the ladder toward the wall at a rate of 0.5 feet per second, well, then the distance between the foot and the wall is decreasing, so dx dt would have been negative 0.5. So we always want to think about when we're given the value of the derivative or the rate of change in words, we always want to take a moment and pause and say, is that positive or negative? Okay, so now what's the constraint equation? So what equation relates the variables, the different dependent variables x and y? Well, that's just going to be from Pythagorean's theorem. So we know that at all moments, x squared plus y squared is going to have to be the length of the ladder squared, which is 25. So this has to hold at all moments in time. And in fact, this is the equation that we use to determine that the height of the ladder at this moment was 4 feet. Recall it only said, the problem itself only stated that when the ladder is 3 feet from the wall, it didn't give us the height at that moment. So we've already used the constraint equation once to determine the instantaneous value of our last dependent variable y. Now to do the related rates equation, we just differentiate this constraint equation with respect to time. So with related rates, we're always going to be differentiating with respect to time, and it basically falls in the same manner as the chain rule or as implicit differentiation. So x we think of as a secret function of time. So x squared becomes like x of t squared. So it's 2 times this x of t to the 1 times the derivative of the inside, so it's times x prime of t. So the derivative of this is going to be 2x times dx dt, so 2x times x prime, plus same thing with y, it's 2y, y prime is equal to 0. So this is our relate, or sometimes you might write it as 2x dx dt plus 2y dy dt, whatever your preference. This second one might be safer because sometimes the prime, you might lose track of, oh, that's x prime and not x to the first or something like that. So this equation is known as the related rates equation. It relates the variables that are changing in time with their rates of change. So it's related rates. You know, one of the rates is dx dt, one of the rates is dy dt, and these rates of change are related to each other by this equation. So we know dx dt, so at this moment, and this equation holds at all moments in time. So at this particular moment where we know the current value of dx dt, we know the current value of x, and we know the current value of y, so we can use this to solve for dy dt. It's also a common factor of 2, which we can divide out. So we basically get x prime plus y prime equals 0. We're looking for y prime. X was 3, x prime was 0.5, and then plus 4 times y prime is equal to 0. So y prime is equal to negative 1.5 over 4, negative 0.25, right? Because 1.5, no, that's not true. I was thinking 6 in my mind. 1.5 over 4, 0.375, so 3/8, minus 0.375. So the answer is that the height of the ladder is decreasing at a rate of 0.375 feet per second, or 3/8 of a foot per second, decreasing at this rate, or the rate of change of the height is negative 0.375 feet per second. So we know, so it's kind of cool, right? We have a physical situation. The variables have this physical relationship to each other, and we know the rate of change of one variable, and we can use that with the constraints and with calculus to figure out the rate at which the other variables are changing in time. So this is a very kind of this is probably the classic related rates problem that everybody does. The first one. And then over the remaining videos, we're going to see a lot more different examples of related rates problems.